Okay, everybody, welcome back. Another quick chemistry video. This one, not really sure, but we'll do maybe part of one. Maybe this might be a two-parter. We'll see. All right, so we're going to talk about really electrons and electron configuration. And really, before we could get into that, we need to know where electrons are in the atom. So we're going to talk a little bit about here energy levels. We're going to talk about orbitals, kind of the order that electrons go in there. And we'll see where we are in terms of time at that point. We may again continue into a second part. Dare I say the second part quick video. We'll see here. All right, so let's talk about electrons. Electrons again in the atom, outside the nucleus, flying around pretty randomly. Don't really know the path, really know their location. Heisenberg's uncertainty principle there basically tells us that a particle like an electron, we don't really know at any given time exactly where it's located, exactly how it's traveling. The best we could do is more like a probability of, there's a pretty good probability of finding an electron in a certain location within the atom. Not really sure how it got there, not really sure how it's moving, but just there's a pretty good chance or probability of finding it. What we do know is overall the nucleus is positively charged because it does have protons in it. Electrons are negatively charged, so there definitely should be some attractive force between those. And there should be a fairly good shot at finding some electrons around the nucleus. Once again, electrons don't travel in pretty little circles and orbits or anything like that. We move away from orbits when we talk about sort of electron configuration, and we talk about them in these sort of probability maps as being located in what are known as orbitals. And there are several different types of orbitals where we can hypothetically find electrons, if you will, in an atom. There are s orbitals, and s orbitals, for the most part, have a spherical type shape. And there's pretty much only one type of s orbital. No matter what energy level you find an s orbital on, they're pretty much only find one type. And for purposes of this sort of diagram, I'm going to represent that as just like a line there. That line there is going to represent kind of an orbital. We also have p orbitals, and they're kind of like figure eights. Sometimes people sort of describe them as, there's actually three types of p orbitals. There's actually a px, a py, and a pz orbital. They're basically located on like math, like the x, y, and z coordinate plane in sort of three-dimensional space, kind of heading in opposite directions. That's a very badly drawn plane right there. But again, you got one kind of going this way, you got one kind of going this way, and you have one kind of going this way there. Not the best drawing, perhaps why I'm not an art major. All right, so we have three different types. So when we're talking about p orbitals, there's really three of them on any energy level that kind of go together. We also have d orbitals, which kind of for the most part look like a couple of p orbitals put together. I'm not going to draw with this, probably where my art skills drop off pretty badly here. So we're going to put two kind of p orbitals together, but really there are five types of d orbitals, excuse me. We have 1, 2, 3, 4, and 5. And again, for purposes of this video, we're not going to get into sort of their designations. Probably for most of you watching, it's not all that important, so we won't get into that. Here for f orbitals, they kind of also look like a couple of d orbitals stuck together. And again, there are 7 types of f orbitals there. I'm in trouble there with the alphabet. 1, 2, 3, 4, 5, 6, and 7. Yeah, kind of squeeze that guy in at the end there. And these orbitals, again, are really sort of like, if you want to think about it, kind of probability maps of where you could find an electron within an atom. Now, when we talk about orbitals in general, any individual orbital can hold 2 electrons maximum. So any individual orbital, in my little pictures here represented by these little lines, can actually only hold a maximum of 2 electrons. So for example, if I use electrons represented by arrows, I could only put basically 2 of them in. to one orbital at a time. For example, here we could go here, 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 and here. Again, each of the individual p orbitals, for example, this being our px, py, and pz orbital, they could only hold, again, 2 electrons each maximum. So these orbitals, S's, P's, D's, and F's, are within the atom where we house basically our electrons, where they kind of fill into as we go through and sort of fill the atom with electrons. Each individual one, again, could hold only 2 electrons, like I said. That also brings us to energy. And when we talk about electron configuration, we talk about energy. N sometimes pops up. And N is the principal quantum number. And N is the principal quantum number. That is a pretty fancy way of basically saying the energy level. So when you see this N number, it is basically the energy level. There's actually 4 quantum numbers, and probably most people watching this video won't have to deal too much with those 4 quantum numbers, unless you're taking maybe first semester general chemistry, in which you do, but we're not going to get into that in this video at all. But we are going to talk about N, which is the principal quantum number, and that is basically, like I said, the energy level. N can have values basically 1 through 7. N is equal to 1 was sometimes referred to as the ground state. That is the lowest state of energy. That is pretty much as close to the nucleus as you could get. Now, anything above that, kind of N equals 2 through 7, sometimes referred to as excited states. And that is something that is higher in energy. So how does the energy levels sort of relate to our orbitals and electrons? Let's talk a little bit about that, I think. So energy levels are where we find these different orbitals that we just talked about. Now, how electrons go into the atom is always it feels from lowest energy to highest energy. So for example, if we have N equals 1, which is basically your lowest energy state, closest to the nucleus, on that energy level, the only orbital present is what is referred to as a 1s orbital. That is those s orbitals we were talking about a second ago. They start on energy level N equals 1. So on N equals 1, that is where we see our s orbitals, and it's actually the only orbitals that are present on the first energy level. You will also see s orbitals on every other energy level as you go through it. It's not until you get to the second energy level, we again will have an s orbital on that, which is referred to as a 2s orbital. You might be catching on right now, that number in front represents the principal quantum number. It represents the energy level. So a 1s orbital is basically telling you I'm on the first energy level and I'm hanging out in the s orbital. A 2s orbital tells you I'm on the second energy level and I'm hanging out there in basically an s orbital. But on the second energy level, that's actually where we first start to see our p orbitals appear for the first time. And those are what are referred to as the 2p orbitals. And that is where we see, like I just said, that is the first appearance of p orbitals once you get to the second energy level. Remember, there are 3 different ones, our px, py, and pz orbital. And that is where we first start to see those guys appear. Coming to the next energy level, N is equal to 3, we again still see s orbitals present. We still see p orbitals present, which would be at this point, since we're on the third energy level, 3p orbitals. And this is where we first start to see our d orbitals appear. Remember, there are 5 different d orbitals represented by these lines, and this is what's known as the 3d orbitals. And our d orbitals, as we just see here, starts on the third energy level. So it's not until the third energy level that you actually get some d orbitals available to you. If we continue on here on the N equals 4, We have, again, our s orbital still present, now a 4s orbital because it's on the 4th energy level. We have our 4p orbitals available because they're on the 4th energy level. We have our set of 4d orbitals available to us because they're on the 4th energy level. And on this 4th energy level, this is where we first start to see the appearance of our f orbitals. And these are our 4 f orbitals. So our f orbitals begin on the n equals 4 level. We could continue on, but I'm not going to continue on. But same thing, n equals 5. You know, we have our s's, our p's, our d's, and our f's as well, and so forth. So this is really important. Once again, energy is increasing here as we go up. So obviously the first energy level, n equals 1, is lower in energy than the second, which is lower than the third, lower than the fourth, and so forth. So let's talk about a few other things about these different orbitals and sort of some questions and words that you sometimes hear when people are talking about this stuff. The first one is what is referred to as a subshell. Or depending on, you know, your book or what you're reading, some people also call it a sublevel. So these primarily are talking about p orbitals, d orbitals, and f orbitals. Why are they specifically talking about these type of orbitals? It's because if you remember on the last slide, with s orbitals, there's only one type of s orbital, no matter what energy level you're at. But when we get to p orbitals, there's 3 different types of p orbitals. When you get to d orbitals, there's 5 different types of d orbitals. And when you get to f orbitals, there are 7 different types. So when you take a group of, say, p orbitals, d orbitals, or f orbitals on a particular energy level, those are what are sometimes referred to as a subshell. So for example, if I took all 3 of those p orbitals on the 2nd energy level, that is what is known as the 2p subshell or sublevel. And that 2p subshell or sublevel can hold 1, 2, 3, 4, 5, 6 total electrons, or 6 maximum electrons. Do you have to fill it up? The answer is no, but it could maximally hold 6 electrons. Same thing if I went to the 3rd energy level and took all 5 of these d orbitals together. This is what is known as the 3d subshell. And once again, if we filled it up, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. It could maximally hold 10 electrons. And one more time here, if I come up here to my 4f subshell, all 7 of those different f orbitals together are referred to as a subshell. This would be our 4f subshell. Or again, sublevel. It could hold 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and lucky number 14 there, electrons. So that is 14 maximum electrons. Why do we not call a 1s orbital a subshell? Because again, it pretty much just contains 1 orbital. So we just refer to it as an orbital. That's why we refer to this as a 2s orbital, 3s orbital, 4s orbital, again, because there's only 1. This here, if I just box 4p subshell, 3p subshell, 4d subshell, and again, a subshell or sublevel basically is a grouping of individual orbitals on the same energy level and the same type of orbitals, like the 7f orbitals, the 5d orbitals, the 3p orbitals. Another terminology that is sometimes used is level or shell. And when we talk about a level or shell, we're talking about that n number, basically. And we're talking about all the orbitals on the n number. So for example, if I did n is equal to shell on the n equals 2 shell, which is right here, I'll just redraw it up here. We have a 2s orbital. We also have a 2p subshell. And if we were going to fill up that entire shell, 1 electron, 2 electron, 1 electron, 2 electrons, 3 electrons, 4 electrons, 5 electrons, 6 electrons, that would be a grand total of everybody on that shell. It would max out in this case at 8 electrons maximum. If I did it for the n is equal to 3 shell, our level, there is on that one a 3s orbital, a 3p subshell, a 3d subshell, which if we max out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18 electrons, it would max out at 18 electrons maximum. So if you're asked how many electrons on a particular shell, they're talking about every single orbital on that particular shell. You could count them up. Who wants to count them up sometimes? You probably don't. So if you're asked that question, like how many electrons could you put on a shell or level, you could actually use this equation here, 2 times n squared. N is that principal quantum number. You square it, then times it by 2. So for example, the one we just did, that is the third energy level. We would take 2 times 3 squared. 3 squared is 9. 9 times 2 is 18, right? Because that's basically 9 right there. 9 times 2 is 18. We did our second one. That would be 2 times 2 squared. 2 times 2 squared is 4. 4 times 2 is 8, which is how many electrons we could put in there. So if you want to kind of quickly figure out on a particular shell without drawing it out how many electrons it could hold, that's your formula. Again, you want to square the n number first and then times it by 2 so that you get the right math. Now, another question might be popping up as you're watching this, as I'm kind of putting the electrons into these orbitals. You might be asking, why on subshells like the p subshell, and I'll just kind of redraw like a 2p subshell, am I going one at a time and kind of coming back and then pairing them off? And there is actually a reason for that. That is what is known as the Pauli exclusion rule, which again, we're not going to get into detail in this quick video about it because it won't be a very quick video at that point. But basically the idea is these electrons have spin, and there's those 4 quantum numbers I talked about earlier. And one of them is what's known as the ms, or was sometimes referred to as the spin quantum number. And basically when you have an electron pointing upwards, represented by this arrow, it has plus 1/2 for the spin. And when it's pointing downwards, it's minus 1/2 for the spin. And by doing that, where they're kind of spinning in opposite directions, that allows you not to violate what's known as Pauli's exclusion rule. And that will give each of those electrons within a single orbital what is known as 4 different quantum numbers. Probably outside the scope for a lot of you watching this class or this video here. But that's the reason why. So just a general rule is if you have any of these subshells where there are multiple orbitals present and you had to draw these guys with the arrows, which by the way is referred to as orbital diagram. And in the second part of this video, maybe we will do some of that as well. You always go one at a time in the upwards direction until you can't go any further. And if you need to, then you go back and you start pairing them off in the opposite direction. And that's how you basically fill them. All right, so last thing I think we're going to cover in this video, so it's not a long video versus a quick video, is the order. So what we saw on the previous slide was when you look at the orbitals, say on the first energy level, the second energy level, the third energy level, they were all equal to each other. And that is true when we have basically one electron, like in hydrogen. Everybody on the second energy level, n equals 2, like the 2s and 2p orbitals, are exactly identical to each other in terms of the energy of all those orbitals. So they're all exactly identical. And then you go to the third, they're all exactly identical. But what happens though when you get multiple electrons in an atom that show up, it actually moves around the energy level of those orbitals. So for example, roughly drawn here, you have your n equals 1, you have your 1s orbital that is lower in energy than, say, your 2s orbital, which is lower in energy than your 2p orbital, which is lower in energy than your 3s orbital, which is lower in energy than your 3p orbital. And now you would be thinking, well, 3d would come next, right? Because that's how it kind of goes. And what actually happens, for example, is the 4s orbital is actually lower in energy than the 3d subshell. And there's some other differences like that, but that's very common what you find when you get multiple electrons in an atom. The s's actually are lower in energy than d's. Why is that important? Because again, electrons are going to climb into the atom, lowest energy to highest. So when we get up to going past the 3p orbitals, the next electrons actually go into the 4s before they will actually fill the 3d orbitals. So it does go that way. The s's come before the d's. Once you get past kind of 4s, 3d, 5s, 4d, it kind of follows that pattern as you continue on. So how on earth can you remember that if it doesn't really go in order of the numbers? Most of the time when you write electron configuration, which we'll talk about in the next video, you do it based on filling order. And you can basically figure out the filling order by a chart that you can make pretty simple for yourself. And to do that, all you have to remember is what we talked about, which is our s orbitals, they start on the first energy level. Our p orbitals start on the second energy level. Our d orbitals start on the third energy level. And our f orbitals start on the fourth energy level. If you remember that, and you remember as well that the maximum number of electrons that you could put into these orbitals or subshells is 2, 6, 10, and 14. You're super close to being able to write any electron configuration you would need. So how do we get to that chart that helps us get the order? Well, this is the way I would probably do it. We know that the s orbitals start on the first energy level, so that's a 1s. Next is the p that don't start until the second energy level. You go down to the right a little bit and put a 2p. Next is the third energy level. That's where we see d's. Down to the right a little bit, put a 3d. And fourth energy level is where we find our f's. Down to the right a little bit and put a 4f. At this point, all you have to do is essentially fill in the numbers underneath it. 2s, 3s, 4s, 5s, 6s, and 7s. And again, you can basically just continue that pattern. That's going to be a 3p, a 4p, a 5p, a 6p, a 7p, 3d, 4d, 5d, 6d, 4f, and 5f. And maybe I'll just kind of bring that f down just a little bit here, just kind of put it in line. And this will give you pretty much the order that you need to write any electron configuration. How does this work? You always start up here at the top. You basically follow the arrows. So you go this way, you go this way, you zigzag back, you come this way, and you continue this pattern. You can see right here after the 3p, boom, I'm hitting the 4s, then to the 3d, then to the 4p, then to the 5s. And you can continue this pattern, 5s, then to our 4d, 5p, and so forth. And you can continue the arrows all the way down there. and you'll get obviously the correct order in this case. So this little chart that you can make pretty much by just remembering where each of those orbitals basically begin: 1s, 2s, 3s, 4s. I'm sorry, I said that wrong. 1s, 2p, 3d, and 4d, where those guys start. You can basically recreate this, and you'll have basically the order for electrons. And again, whenever you're writing electron configuration, you always start here, and you just keep zigzagging back and forth. So just to give you kind of a quick example of what we would do here, for example, let's take a non-highlighter and grab a pen. There we go. So for example, we're going to write electron configuration, and like I said, we'll probably do a second part to this video. Let's just say we want to do our friend, we'll do nitrogen, which is 7 on the periodic table. That means it has 7 protons and should have 7 electrons if it's neutral. We would start right here, and we would follow this pattern, and that would first take us to our 1s, and we could put 2 electrons in there. But we need 7, so we got to continue. So we'll come back this way. Next spot is 2s. This would be 2s2. That is only 4 electrons if we count the top. That is 2 and 2 is 4. We still need 3 more, so we got to continue on. Boom, we're going to hit our p subshell next. 2p3, 2 here, electrons on the first energy level, 2 electrons on the second energy level in the s orbital, and now 3 more electrons in the second energy level in a p orbital. Gives us a grand total of our electron configuration of 1s2, 2s2, 2p3, which is our 7 electrons here for nitrogen. And again, on the first energy level, basically has 2 electrons. On the second energy level, which is both of those, again, 2 and 2 is the energy level, that first number, we got 2 and 3, which is 5 electrons on the second energy level here. That is basically when we look at an electron configuration written something like this, that number there is that principal quantum number, basically the energy level. That is the orbital, our subshell the electrons are in, and that is how many electrons are in that orbital or subshell. All right, so like I said, we're going to cut it off here so it's not super long first part of this video. I think there will be a second one coming with a little bit more electron configuration, and I'll try to tie it up here. A link to that here into this video. Once again, thanks for watching. I hope it helped. And again, if you want to see other topics, just let me know in the comments. And that'll be it for now. Bye-bye.